Hi everyone, welcome to my presentation today. My name is Les. I am a principal software engineer with Audere. Audere is a nonprofit organization primarily funded by the Gates Foundation. And today I'm going to be talking about fast-tracking COVID, malaria, and HIV testing, leveraging synthetic data. To acclimate you, on the bottom left here, I've got an image of one of the many COVID RDTs, or rapid diagnostic tests that we work with. And this is an HIV diagnostic test here, and it's a sample screenshot from one of our mobile applications. So, important point to note is that these are in fact synthetically generated images. They're not actually photos of the actual diagnostic tests. All right, to start, we're going to go way back in time just to give you some general context with these diseases. We'll start with COVID-19. Obviously, COVID-19 hit and basically caught the entire world off guard. However, recent research has produced some interesting insights that predecessors to the current coronavirus actually have affected humanity off and on as early as 20,000 years ago or 5,000 generations ago. So this chart over here is basically showing you different waves of interactions with the great, etc. Grandfathers of the current coronavirus. And so the main one of significance was, as I mentioned, 20,000 years ago. And this is basically by looking at lung tissue adaptation, specifically with the ACE2 receptor interactions, and how human genome has tried to adapt in order to deal with coronavirus interactions. And on the left, we have an electron microscope image of an actual coronavirus virus. Next, we're going to go even further back in time and discuss malaria. So malaria is one of the oldest foes, so to speak. It actually began evolving roughly 100 million years ago, so literally in the age of dinosaurs. Modern malaria as we know it, spread via mosquitoes, was roughly began evolving about 8 million years ago. And one of the interesting takeaways with malaria is that, especially in ancient times, no matter your position, you were very much still vulnerable to malaria. King Tutankhamun died of malaria, so in that time being effectively a god king still didn't help protect you from malaria. Two interesting photos to go over here. This is a multi-million-year-old mosquito trapped in amber, and what they found is there are oocysts here still. So this is showing, again, a mosquito at dinosaur times infected with malaria and at the time transmitting malaria. The way the basic process works is that well, if you see this photo down here, these are oocysts, and they are feeding off of the intestinal tract of the mosquito. These will basically grow or incubate in here. They'll burst open, and then they'll swim up from the intestinal tract and work their way back up to the salivary glands, and then from there, of course, get ready to spread into their next host. And moving forward to a little more modern times, so we're up to the 1920s here, HIV. So HIV was developed when SIV, simian immunodeficiency virus, jumped from chimpanzee to human. The working theory, or very likely theory, is that hunters hunting chimpanzees basically became infected by blood from the chimpanzee, getting into cuts that they had on them. So it was effectively human eating of chimpanzees. There were multiple jumps in that time frame in the 20s of human or chimpanzee to human, and that's why you have multiple different strains of HIV. A little interesting backstory on it is that chimpanzees themselves became infected with the SIV by eating other smaller monkeys, and basically from that became infected with two different SIVs. So HIV effectively began evolving 1920s in Congo, Africa. And now to current times. Obviously, as you're well aware, the world was largely unprepared when COVID hit. So pandemics, of course, aren't new, but we definitely were not expecting COVID. To put some things in perspective, in February 2020, the initial approach by the CDC was if you wanted to test for COVID, you were going to be required to do your sample and ship it second day FedEx to Atlanta to test and basically wait for your results. So obviously that brought about significant concerns over efficiency and scalability and parallelization for that matter, but in effect the ability to contain a rapidly spreading disease became questionable. Moving forward in time, spring of 2020, as you may remember, we had significant backlogs even though the CDC began to release its sort of chokehold on the testing environment. Still ended up having massive traffic jams with people waiting hours in line to get a COVID test. And of course, even after you got your COVID test, as this headline shows you, you could end up waiting weeks for your result. Furthermore, COVID has had a very negative impact in terms of the other diseases we're discussing, for example, HIV and malaria. So one of the reasons was just the supplies of reagents needed for traditional lab testing are also needed for HIV testing. And with COVID, of course, you had health workers unable to reach different sections of the population due to quarantines and so forth. So this chart over here really shows you the impact. This is the reduced amount of HIV testing that occurred as a direct result of COVID in Africa. And so I'll just highlight this quote over here from the Global Fund that COVID has been the most significant setback in both HIV, TB, or tuberculosis, and malaria in the 2 decades since the Global Fund was established. Other thing to point out with malaria, COVID of course is devastating, but malaria continues to rage on, especially in Africa. The WHO is estimating 94% of all global deaths from malaria do occur in Africa. And probably the most depressing part of that is that children under 5 make up the majority of deaths from malaria. In 2019 numbers, we had 229 million cases and 409,000 deaths. So, another quote here from WHO, likely that excess malaria mortality is larger than direct COVID-19 mortality, so significant impact. So the question then becomes, how do you rapidly detect these diseases, do it at scale in order to save lives? And the current optimal solution is basically moving a lab process into a small box, that small box being an RDT. So RDT stands for Rapid Diagnostic Test. And effectively, that allows you to scale up detection. You decentralize and you scale it up by moving the different lab processes into a compact, repeatable, and portable process. So this is an example of a prototype COVID test in development. But what you have is the entire lab process becomes all contained into a small device. In some cases, you sacrifice a small bit of accuracy, but it does give you massive ability to scale. Other thing to point out is RDTs are consistently improving, and some of them are very much an exact match or extreme match for the accuracy of lab testing as well. So this gets us into some of the clear advantages that are available with rapid diagnostic testing. As I mentioned, we've got massive scale, ability to parallelize. Portability, of course, increases access to these tests. You no longer have to go into a central facility. It can be done at home, mobile sites, mobile clinics, etc. Faster detection and easier monitoring. There's also reduced workload on healthcare workers, and cross-infection risk, especially with regards to COVID, is reduced. That cross-infection risk and reduces supply of some of the safety things like PPE, personal protective equipment, and some of the labor costs there. So over here I've got just some different RDTs. So this is COVID and COVID, and a couple of malaria ones as well. One thing to point out that while a lot of people are not familiar with RDTs proper in terms of malaria, etc., you probably are familiar with pregnancy tests, and that is of course an RDT. And the accuracy of pregnancy tests is such that your doctor pretty much will not require a lab test if you have taken a at-home pregnancy test. The accuracy is there, that there's no need to repeat it with a laboratory process. So as I mentioned, RDT accuracy is continuing to improve, and some of them already currently fully match lab processing accuracy. And now we'll move into how RDTs work internally. They're obviously quite small by design, but they actually do have a pretty complex process that's going on underneath to detect disease. So if you look at this chart over here, basic process moves from left to right in kind of a pipeline fashion, and starting with the left, you end up submitting your blood or saliva solution that gets mixed with a buffer solution, and that creates a fixed amount of fluid volume. From there, it'll get drawn forward via capillary action, and the first major stop is what's called a conjugate pad, and that has been spiked during manufacturing with an antibody that will produce a visible result, typically gold nanoparticles. That moves forward that whole mix into the most important part, which is this here, the test line or test zone. And if you can see this down here, if I'm not blocking it, you end up with a two-stage reaction where the viral particle plus the marker antibody plus the test line antibody produce a bond, and as such it will produce a visible reaction here. And then you have the control line. This will only match directly with the visible antibodies, and what that does is if this gets signaled, then you know that the process moved through the test zone, meaning that you have a valid test. So that's the basics of how it works under the covers. As I mentioned, the chemistry of the RDT can be extremely accurate, but we do have a significant gating factor, and that is human reliability and or expertise. So specifically, we have the problem termed human variability. That plays out in many forms. We start with what's called accurate administration, and that's simply, for example, putting the right amount of buffer solution along with the sample to be processed, processing the timer that's involved. There's typically a 15 or 30-minute wait time and then a read window time. You do require understanding and training on how to interpret the visual signals that are presented by the RDT. You have limitations with the human visual system in terms of its ability to see faint lines, which we're going to get into here in a minute. You also have to believe that they are there, especially in the case of faint lines. That gets into some stuff we'll talk about with cognitive dissonance. But basically it boils down in many respects to the consistency of the interpretation, i.e. the no bad days. So health workers also have a dilemma that they've got a lot of RDTs that have different lines that mean different things. So that can create a lot of variance in and of itself. Wanted to show you over here on the right, these are some COVID tests, and of course these are very bright, clear, easy to read lines, but what these are is the control line. And as I mentioned, the control lines are display antibodies that are highly spiked during the manufacturing process, so you can very consistently get nice readable lines on the control part, but that is not the hard. Now we move into the harder problem. The control lines, as you saw, were quite easy to read. Now we get into the test lines, and it's not so easy. So over here, what I'm showing you is all positive results. These are all positive COVID tests. And as you can see, this is the test line, and its ability to visually see that varies quite a bit. We have a lot of faint lines in this case. And the reason for that is that the signal that's produced is basically a direct mapping of the viral load. So it does not the RDTs typically do not amplify the viral signal. So for example, if you have one viral particle out of a million particles in the solution, that's still very much a positive, but you're also going to get a very faint result. So again, extremely faint line is still very much a positive. So some of the studies that have come out on this, one study actually found that the most effective improvement for improving RDT accuracy was not actually improving the chemistry itself. It was ensuring that the doctor or person reading actually had an up-to-date eyewear prescription, preferably within the past 6 months. So similarly, an HIV study showed that the human ability to correctly read the HIV RDT varied pretty widely, 80 to 97%. That wide variance is kind of a result of many potential things, but short-sightedness, color blindness, those type of things. The other thing that I mentioned is cognitive dissonance in terms of a person self-diagnosing, especially for a deadly disease like COVID or HIV or malaria. You psychologically don't want to see that line. Here we've got some very extreme examples. These are all positive COVID cases, but what you can see is that these are in fact visually very much appear quite blank or negative. Now, when you view them under a visual enhancement that we developed at Audere, you can see that all of these are in fact very much positive. So this is sort of a X-ray-ish type system in terms of building confidence, particularly in our AI systems, but what it does show you here quite nicely is that what you see visually can be very different than what's actually there. So this brings in the involvement of AI, artificial intelligence, and the question, of course, is how can AI help solve this human accuracy and scaling up of expertise problem? So one of the studies that has been done on comparing AI results with human results was an HIV study, and what they found was the AI was 98.9% accurate, and the human expert reads were 92% accurate. So you've got a big potential jump in terms of accuracy there with AI. Another one that was actually related to pregnancy RDTs, talks about the cognitive dissonance or self-diagnosis conflict I've mentioned. And what they found was a person reading an RDT with no interest in the result or the outcome, they were 91% accurate, so very similar to this 92% we see here. But when it came to reading their own RDT or where they had a vested interest in the outcome or conflict, it dropped to 75%. So some of the big advantages, of course, with AI, it's repeatable. It can scan pixel by pixel by pixel ad infinitum. By contrast, humans, of course, are going to get tired and distracted, and as we've seen, can be prone to very large variance. Other thing, as I mentioned, not all human visual systems are the same. The GIA found a specific demographic actually had the best color accuracy. This is really just diamond grading, but it's very interesting. But that was just due to the cone rod density of that particular demographic's eyes. By contrast, 1 in 12 Caucasian males actually have some degree of red-green color blindness. This is some internal study we did. So this is flu diagnostic, and we had a panel of 10 experts reading it, and it was compared to our AI interpretation. And the results, numbers were 95% versus 57% accuracy, but the numbers don't really tell the full story. This chart over here tells you a lot more of what happened. Specifically, going from left to right, we're moving from high viral load to low viral load, but still positive. And as you can see, the first two viral loads here, humans and AI, are basically 100% accurate. But from there, the human ability to interpret begins to rapidly plummet as we lower the amount of viral load. So AI continues all the way out, in this case, to dilution 6, and then slowly begins to drop off. So this gold area here is representative of the gain that you get leveraging AI in place of human. So this chart here is an overview, kind of the Audere pipeline and what we work with. Specifically today, though, of course, we're talking about digital capture and automatic interpretation via AI, but I just wanted to show that this is part of a larger system in terms of the whole healthcare process. All right, now we get to the most exciting part, in my opinion at least, and that is discussing how do we build an AI system for RDT diagnostics. The first and foremost item that always has to happen is, of course, data collection. So you need lots and lots of images to train your AI system. For RDT diagnostics, we have some particular requirements. They're typically done in a lab environment, and from there you spike a lot of RDTs, to thousands of RDTs with different viral loads. That gives you different line intensities, and you bucket those into categories. And from there, you take thousands of images using different lighting and so forth, and that lets you train your computer vision or AI pipeline. Of course, immediate drawbacks are that's time consuming. It's also very costly. There's limited openings at biosafety labs to do this work, and surprise, governments actually aren't exactly enthusiastic when you are importing COVID blood, especially during a pandemic. So within the architecture itself, though, we have the AI pipeline and how that breaks out. And there's really two main sections or components to it because it has two main goals. First thing is to find the RDT that's in the image and determine what type it is. So that's the object detection portion. And this is exactly what's happening here. So this is a malaria RDT. Object detection has already been run on this. You can see it's basically sectioned off all the different subsections of the RDT, and you've got the confidence levels displayed in this image. From there, we're going to zoom in to what we really care about, which of course is this diagnostic section here. And that's the classification phase or interpretation, where we actually need to interpret what is the ultimate diagnostic result from this particular RDT. One of the most important limitations with AI is that it will learn exactly what you show it. So that comes into play with what are termed out of distribution failures, if you do not account for that. So one of the classic examples of that type of failure is the facial recognition software you might have heard about, where it did great, had a 0.7% error rate, so very high accuracy, and deployed that to the real world. And what they found was that, in fact, that 0.7% error rate actually only applied to Caucasian males, which was the primary component of their data set, and bombed with 34% failure rate for dark-skinned females. So for us, some of these confounding factors that we have to bear in mind, I've got some images over here to exemplify that. This is an example of a malaria test that came in from Africa, and what we see is a lot of dirt scattered around the test. We've also got some shadowing over here, but of course the big difference between a biosafety lab, which is a very pristine, sterile environment, and the real world is you can end up with things like random dirt being scattered on there, and your AI has to be able to deal with that. Over here on the far right, have an example of excessive blood leakage in the channel. That's not a common thing, but it is 5% type of scenario. And so what we have here, this is a positive result, by the way, but the background, instead of being the high contrast white you would expect, is now a very pinkish background, which greatly obscures the positive result and has an impact in terms of how the AI has to be able to deal with it. Down here, we have a misadministration. So this dark tobacco colored stain is either the result of too much or too little buffer solution being applied when they ran the test. It is a positive result. We've got the part of the test zone being lit up here with the pink, but very different look that the AI has to be able to deal with. Over here we have an issue of scale difference, and so this is a field worker who's basically done the best they could, which is drop the notebook down and provide some kind of basic background, but of course completely different scale than in the lab. Over here is a intensive shadow coming in likely from sunlight. Got a faint positive result there, but literally half the thing is dark because of the sunlight factor. Last one I'll show you up here This interesting one, this is a COVID test, and it is a positive result. You see this little faint blue gradient right there, but instead of the normal line, it's just this faint blue thing. So this is sort of the half-line problem, as we termed it. And what happened here was about 1 in 1,000 cassettes where our RDTs were actually doing this, but our AI had only been trained on full lines, so we had to understand and deal with this half-line scenario. Our most effective method of choice for generating synthetic images for detection is we will build the RDT using Blender. So we create an exact virtual replica, and then we import that into Unity Perception, and then using that we can generate labeled data sets for training our object detectors. So the advantage of that is, of course, we can completely randomize the backgrounds, and that deals with the potential almost infinite variety of backgrounds that could be used for a given user or clinical image. And then this example of it over here in process, so we have what I call the board wall, and that's basically an amalgam of different textures and shapes, and we've got our COVID tests being randomly scattered about, and then that will be one single image of many images that we'll train the detection system on, and this is showing the design environment in Unity Perception. We can do things like randomize shadows, representing a head, for example, impacting a curved shadow on the RDT. And one of the most important things for us is we can replicate sunlight very accurately. We can, in fact, get down to doing exact sun position for actual locations, for example, a specific town in Kenya. Also is very effective in terms of turnaround speed and being able to deal with, a lot of times you'll have rapid changes in the interface for a given RDT before it goes into deployment, and so dealing with that, we can randomize the stickers and the QR codes and all those good things on the RDT itself in the synthetic world without having to do the exact same thing in physical world. Continuing with the benefits from synthetic data, we've been able to see significant improvements in the robustness of our AI pipelines, especially dealing with things like sunlight shadows, and we're typically leveraging an 80% synthetic mix and 20% real, while providing equal or greater detection accuracy. But the most important part is that's using up to 4x less real data, so some significant both cost and time savings there. It does enable us to deliver to market much faster. Classic example that we had was after a pipeline was nearly ready to go, data set was done, models were all trained, and due to some other issues, they suddenly had a requirement that they were going to be employing stickers on top of the RDT as it moved through their clinical processes. So of course we had no idea how the AI was going to deal with that. But rather than having the normal scenario, which would be 3 weeks of getting the cassettes, producing 500 to 1,000 RDTs with lines with the stickers on there, we were able to test that out, and in 3 days, given the answer that we could handle that, and that was done entirely synthetically. Probably one of the most exciting developments now is that we are able to have working AI systems already up and running even before we've actually received, or the biosafety lab has actually even received the cassettes or RDTs to make the photo data set. And this image down here is exactly an example of that, and I'll show you more in the videos. But this is an HIV test that was, object detection has been run. The model for the object detection was entirely trained on synthetic only, and now we're dealing with actual live images and doing a great job. Over here is another example of the precision we've achieved by combining synthetic plus real world data. And on the top left here is a synthetic image showing you, this is a sunlight image, but showing you the effects of a head or a person's head as they are taking a photo of the RDT. And same thing down here, these linear shadows can be very problematic, and so we're replicating that synthetically. In this case, we've got it where the T-line or test result could be potentially confused by the AI because we've got an express dark line shadow there that could replicate a positive result. Moving into the second portion of our AI pipeline, which is the classification section, so in other words, interpreting the diagnostic strips. We are now able to generate near photorealistic images for our classifier training. These images all over here are synthetic imagery of diagnostic strips, and that allows us to produce very hard to reproduce physical results, extremely rare and valid cases. For example, the best example is, of course, when I showed you that photo earlier that had the half-line situation. So instead of a full line, it was generating only, well, really more like a quarter or eighth of a line there, but it's still a positive result. That was only happening in 1 in 1,000 physical cassettes or physical RDTs. But to generate a training set against that with real images would have meant, tens of thousands potentially of RDTs. spiking those with viral load and hoping to get your 1 in 1,000 scenario to take images of that for training your AI. So our solution was initially using GANs, and then we moved into substance graphs. And the difference is that GAN will take you days to train, and you do need some form of a seed set. With the substance graphs that we're using now, there is no seed set needed whatsoever. The most important and exciting development that we're seeing is that with these photorealistic or near photorealistic data sets we're able to build synthetically, we can train our systems, and they, having never seen an actual RDT in their lives, run them against holdout sets of COVID or malaria real world RDTs, and we get an average of 95% accuracy right out of the box, so to speak. So very exciting developments there. So it all comes together with end-to-end training, and I'm going to get into some videos here to sort of put all this together and let you see what's actually happening. All right, here's our first video. I'm going to show you basically what our synthetic models look like and how we integrate some of the components there. So what I'm showing here, we've got a lot of detailing, including the fact that it is a two-piece unit. So we've got that seam there, the notching that's done. I was showing the injection port in the back, even though we don't actually leverage the back, but that's the level of detail that we're putting into these models. Up here is what's called the invisible geometry. So basically we're providing the areas that we want the object detector to learn how to detect, and that's the different boxes there, the different zones of the RDT for this specific COVID example. So what I'm showing here is that we've imported a substance graph, and what happens is we can dynamically generate all kinds of variations in terms of the test and control lines. So you can see we've got different gradients we can enable. You'll see that it'll fuzz out in a minute. We can add different types of blurring effects. But the idea is to create sort of a consistently randomized object for the object detector to see. And so all of these variables here, the min, max, and all that will be dynamically randomized during training. And this next video, you can see the vast array of RDT synthetic models that we have to work with. From left to right, we've got a malaria cassette, we've got an HIV cassette here, and bottom left is another HIV test, and another different type of malaria RDT there. So just taking a quick tour of all these simultaneously, but the main point is you'll see that each one of these has individual randomization. So we've got the different parameters for the control lines and test lines and so forth. This one over here is a little bit interesting because it's actually a dot format rather than a line. So that's different. Of course, this one is contained within a test tube type of environment. So you'll see some of the dynamics being applied here. This is representing that gradient or blood fill that I talked about, which is a 5% type of problem. So we can dynamically mimic that synthetically as well. Now we get to another exciting part here, which is the actual generation of the data set. So we take those models that I've shown you earlier, and then we put them into the Unity perception pipeline here. And we're going to start to generate an actual data set for training. So here's the Unity environment. What's happening there, that's that Borg wall being formed that I mentioned. So we've got the dynamic background. In this case, so it's my daughter's homework and pictures of coronavirus and all kinds of randomization there. More importantly, you see the labeling that's going on here, and also you'll see the fact that these translucent spaces, the background's showing through and giving that dynamic, real-world type of feel to it. Transparency is a very difficult thing for detection. And we did extremely well training synthetically for that. This is showing, again, some of the changes that we put here. This is different lighting, so we've got more an evening type of lighting on this particular case, and with the labeling there. And now, generating a data set. So this is 120 images, all within a matter of seconds. After we've generated our synthetic data set, we move into training the detection model. And what I'm showing here is some of the training pipeline. I'm not going to train the model here, but the basics are that we've got some display actions, and we can inspect the labeling and so forth of the synthetic images. Additional factors is I'll apply a whole host of additional augmentations. So if you look over here, we've got the black grid, and we've also further augmented the lighting as well, just in general. So let me get the video going. And I can also turn off the labels, of course, so that allows for some closer inspection. I just want to make sure that everything is as we expect. And this is an example of the synthetic rain also that we put in there to further occlude and provide additional work for the AI models. So with the training done, I'm going to move into running on a actual real HIV test. So we're going to load up the image that we're going to do here. So this is a user scenario. So they've done the HIV test. Going to get ready to put it through the object detector. So that is this step right here. Get our tensors back. And from there, we can, leveraging those tensors, we'll draw out what the results were. And we can see we get a very nice high confidence result, very accurate. And the next step would be to extract the part we care about and vertically orient that. So that's what this is going to show right here. So there we have the most important part of that entire image, and that'll move into the next phase of detection, which is to extract that diagnostic strip. And finally, we're going to move into our final aspect, which is creating the synthetic diagnostic strips. So let me start this video here. This is using substance graph, and what I'm going to show you is the vast amount of parameters that we have to generate a whole host of real-world scenarios synthetically. So as you see over here, this is the test strip that we're synthetically generating, and what I'm showing here as I move the parameters around is all the different variety, the min-max of all the different things we can do to the strip to represent real-world things. So this is, for example, showing randomized dirt, and we've got, in case they have a plastic or glass covering, white balance of the camera. I'm going to show some different shadowing, some of the other effects that we can do there. This gets into the whole blood scenario that I talked about, that blood leakage, so we have different levels so we can control that and create, all the way to full saturation like the image I showed earlier. That is representing the buffer stain scenario. We can also have, sometimes the control pad will leak additional gradient into that, and so we can change the color of that staining. That's the scale of the glass or plastic covering that is on some of the rapid diagnostic tests. Some randomized camera noise, obviously random scaling, zooming in and out, and of course rotation in there. And so what I'm showing here is actually generating a data set for training for the classifier. So this will give you an idea of how rapidly we can do it. And what I'm going to show here is this is the circle-based test, the HIV one that I showed the model of earlier. We built a completely different pipeline for that, and so that this is generating these circle-style tests, and just showing you again a whole different host of parameters that we can have involved there, including obviously different colors, where the dots are, how big the dots are, the background of the membrane that's on there, and show a few more things, and then we'll generate another quick data set. So additional camera noise, and of course different levels of scaling. Show rotation here in just a second. And so that's perspective skew, so if they're tilting off to one side or the other. Some additional blurring factors, and of course rotating the light around. Additional shadowing, and we've got a few more, and then we'll generate. Yep, so here we go. So this is showing you running, creating another data set, in this case for the circular dot type of diagnostics. So again, you can see the speed that we can generate these images once we have these pipelines built up. We can really have an infinite source of data to train on. So hopefully today you've been able to see how we are leveraging synthetic data and its impact in terms of improving AI. So to summarize, synthetic data is basically helping AI move forward along the classic better, faster, cheaper axis for improving global health. To break that down a bit, better means not just improved AI accuracy, but also improved AI model robustness. That's because, as you've seen, we're able to have the models experience a full range of real-world variants, a lot of those which are hard to replicate. Faster, of course, relates to time to market. You can handle changes to RDTs fairly rapidly without having the need to redo expensive data sets. And as I mentioned, one of the more exciting developments is we are currently able to start training our entire pipelines before the physical RDTs have even arrived at the biosafety labs to begin the photo taking process. To put that in terms of numbers and real-world perspective, last year there were 540 million of those RDTs, so that's COVID and malaria RDTs, and that was for the LMIC, so low and middle income countries. And if you take an 8% jump in accuracy from AI and multiply that by your 540 million RDTs that were distributed last year, basically have the opportunity to improve 43 million people's health outcomes per year. So the numbers of RDTs continue to grow, and there will be significantly larger scale, especially on the COVID front, coming in 2022. So that concludes the presentation. Happy to do Q&A. We may have run out of time for that, but some quick footnotes here. This is our organization's contact information, and of course over here is my personal contact information if you have any questions, in case we don't have time for Q&A. Otherwise, happy to do Q&A now, and hope you enjoy the presentation.